Ding dong. The time at the sound of the cursing engineer will be 11:30 a.m. Pacific time. God damn it. Greetings, everyone. Hooray, I'm on. Okay, so this is just going to be a video of me soldering up the ALU for the RISC V processor that I'm building. Now, I have a tester and a backplane, and the tester and backplane are currently being tested by a friend. So I won't actually be able to test the ALU until that is actually complete. But at least I can get a start on soldering this up. And that's probably where the thumbs down came from, because I said beforehand that I was going to pronounce solder like folder and not like solder. So let's see. So the ALU, let me change the camera around so that I can draw some diagrams. Let's see. All right. Going to make everybody a little dizzy, but that's okay. There we go. Let's zoom in on a piece of paper. Focus. Okay. So this is the way that the ALU works. Now, on the backplane, I have 3 buses, a destination bus, and a source 1 bus, and a source 2 bus. And all of these are 32-bit buses. 32-bit buses. So, you know, if you had an ALU, which is typically this symbol here, you know, what you could do is you could connect source 1 up to one of the inputs and source 2 up to the other input. And then there's some sort of a function over here that you tell the ALU what to do, and then the output goes to the destination. And of course, source 1 can come from a register, source 2 can come from a register, you know, or maybe it's an immediate value or whatever. And the destination would typically go to a register, at least in RISC V. The other interesting thing about RISC V is that the ALU has no flags. Normally on CISC processors, and even on some RISC processors, there are flags coming out of the ALU. Things like, you know, 0 if the result is 0, C for if there was a carry out, that sort of thing. RISC V does not have any such thing. So functions are things like add, subtract, XOR, OR, and there's also set if less than. So that's one of the instructions. So how does the ALU actually work? Well, we can start with addition. That's really the hardest thing to do in this case. Oh, by the way, there is no shift that I'm putting in the ALU because shift is a fundamentally different operation from all of these. So that's actually going on a second card. Okay, soldering. We are soldering soon. Okay, so with an adder, you know, there's the typical full adder with a carry in, and you get, you know, 1 bit, I'll call it A, and another bit, I'll call it B, and the output, I'll call it X, and you get a carry out. And a ripple adder basically just connects a whole bunch of them together in a line, like this. Full adder. Okay, so if this is, you know, A0, A1, this is going to be a 31 in my 32-bit bus. Okay, so we have 32 outputs. We've got a carry out, which of course we don't do anything with because RISC V doesn't have a carry out. So the idea here is that the full adder computes the sum of the carry in, the A and the B, and outputs a sum bit and a carry out bit, and that feeds to the next full adder and so on. So the problem is that if this full adder incurs a delay of delta, then you will only get delta from the input of A0 to the output of X0 and also carry out, right? So this is basically a propagation delay of delta. So this would be 2 delta, 3 delta, and so on all the way down to 32 delta. So the longer your the more number of bits you have, the longer your delay is. In fact, your delay is going to be order n based on the number of bits. Now, there is a carry look ahead way of doing things. Oh yeah, you can improve this. You can improve this by having a full adder that actually takes multiple bits at a time. So, you know, this could be A0 to A3, and this could be B0 to B3. This would be your carry in, this would be your carry out. Your sum would be X0 to 3, you know, and the advantage of doing this is that this is probably about the same sort of delay because it probably has the same number of levels of logic inside, maybe a little more, but at least you won't have 32 full adders. Let's call this a quad full adder. Instead, you're going to have just 8 of these, so you will incur a delay of 8 delta. Now, again, the delay is order n. Sure, n is, there's a factor in here, but, in algorithms, you don't count the constant factor. It's still order n, so that you know that as you increase the number of bits, the delay linearly is linearly associated with that. So then there's the carry look ahead method. And with the carry look ahead, what you do is, let's suppose again you have our quad full adder, and you have a carry in, and you have 4 bits coming in, 4 bits coming in, and what you do is you have a sum and also 2 bits called propagate and generate. I've gone over this in previous videos, but I may as well just go over it again, because why not? And the idea is that if you have a whole bunch of these full adders, and they're all outputting propagate and generate, and what propagate and generate mean is, if propagate is high, that means that the inputs are such that if the carry in, whatever the carry in is, that's what gets propagated to the carry out. And you can calculate that fairly easily. The generate bit is set when there is a carry out, regardless of whether there's a carry in or not. So for example, let's suppose you're adding, these 4 bits and they're 15 plus 15. Well, the answer is 30. You're absolutely going to generate a carry bit. So you can compute what P and G are just based on the 2 inputs, and that incurs some propagation delay. What you do is you feed all of the propagation and generation bits into a carry look ahead unit. What the carry look ahead unit does is, now look, these are only 2 bits, 2 bits, 2 bits, 2 bits. It computes the logic to generate the carry ins to all of these, right? Because all you need to know for the carry in of the next unit is the carry in of the previous unit and whether it's going to propagate that carry in or whether it's going to generate a carry out. So this will incur just a delay of delta, right? Because this isn't a ripple, this actually just takes all of these bits and computes all of the output bits all at once. Once it does that, so we have delta here, and then of course we have these outputs. And these outputs are going to incur another delay, right? Because once you put the final carry into a full adder unit, you have another propagation delay until you get the final output. So in this particular case, it doesn't matter how many of these you have, as long as your carry look-ahead unit is big enough, you only incur a delay of 3 delta, and that is order 1. In other words, it does not matter how many bits you have. Now in practice, these carry look-ahead units will end up being limited by the number of bits you put in, because the more bits you put in, the more complex the logic gets. So you could actually end up with multiple carry look-ahead units. And interestingly, the equations of a carry look-ahead unit allow you to take multiple carry look-ahead units and feed them into a carry look-ahead unit. So if you end up in that situation, then basically you get another delta for this carry look-ahead unit, and then another delta for this carry look-ahead unit, which generates the bits. So I think it's, what, 1, 2, 3, 4 delta? And you still end up with order 1. The logic gets a little more complicated, and of course the logic is lots more complicated than just a ripple adder, but at least your output isn't order n, it's order 1. Does that make sense? I hope that makes sense. And you can look at online, especially on Wikipedia, about carry look-ahead units, and it talks about the equations. So it's a really useful thing to know about. All right, let's see, what else should we do? Okay, so that is an adder. Now a subtractor, basically what a subtractor does is it modifies the second argument to basically invert it. And instead of a carry in, you have a borrow in. Same concept, so you can use basically the same circuitry, it's just that you have to have a little bit of extra circuitry on the other input, and basically that tells you whether you're doing a subtraction or an addition. Now once you have subtraction, you can also do comparisons, right? Because if you want to determine whether A is less than B, then all you have to do is compute A minus B, and if that's less than 0, then A is less than B. I think there's also another bit for signed and unsigned comparisons, because of course if you have, say, let's suppose you have a 16-bit input. So your inputs, could be 0, 0 to FF. Well, in signed arithmetic, you have a range from, I think it's 8, 0 to 0, 0 to 7F. So this is minus 128, this is 0, and this is 127. So that would be it in signed, and of course in unsigned you can represent numbers from 0 to 255. So if you do a comparison between two numbers, if you want to compare is 0 less than FF in unsigned, then the answer is yes. But if 0 is less than FF, which is minus 1, in signed, well, then the answer is no. So there's an additional bit in here to determine whether you're doing a signed or an unsigned subtract, or a signed or unsigned comparison. All right, so that's the circuitry. There would also be other inputs to here, saying whether you're just doing a logical XOR, or a logical OR, or a logical AND. So it basically bypasses all this circuitry. Or actually just passes it through with the logic, and the carry lookahead unit is basically disabled. It wouldn't do anything. All right. Okay, so you can write the logic equations for this, but there is another method of doing it, and that's called Cadet. Can't add, doesn't even try. And what this does is, instead of a full adder, so here's a full adder, here's the carry in, here are, say, 4 bits, input, and you have 2 bits for propagate and generate, and you have 4 bits for the sum. So that's 9 bits in and 6 bits out. So that is a 512 by 6 RAM, or ROM, actually. So instead of actually putting logic here, if your memory is fast enough, you could just replace this with memory. And then your propagation delays will be even lower. And this is not really the case for integrated circuits, by which I mean integrating this into a single integrated circuit. What I mean is a discrete solution, which is, you know, what they did in the 70s and in the 80s, when they didn't really have microprocessors or readily available ones. And that's what I'm doing, because of course my circuit is not on an FPGA. That's how it works. So you can use memory over here. That's for the full adder. The same thing for the carry lookahead unit. The carry lookahead unit takes in, what is it, 8, say, let's suppose it's 8 propagate and generate bits, plus it also has to have the carry in. And then it generates, say, 4 carry outs. Yeah, and that's it. So again, this is a 512 by 4 ROM. So that is what I'm using. I'm using the Cadet model. So the way it basically works is, here are my buses, and then I have buffers here, and then I have one layer of memory, which acts as the propagate and generator RAM. So this is, or ROM, so this is memory. And this is actually divided into like groups of 4 bits. So the result goes to a carry lookahead unit, which is also memory, however many bits that is, which generates all the carry outs. So these are all the carry outs. There's also a carry in, which is not given to it. It's actually generated by the function that is occurring, because when you're doing an add, there is no carry in add, or, you know, like the equivalent of an add with carry instruction in RISC V. So carry in would always be 0 for an add. It's also the borrow in for a subtraction, so that would always be set to 1 for subtraction and for comparisons. So these are the propagate and generate bits. These are the A and B inputs. This is the carry out. That goes to the adder, along with all of these things. So these go over here, and then there's the output. So this is another memory. Now you might ask, well, why didn't I just, and this was actually a bug in the previous design, is that why didn't I just combine the adder with the propagate and generate memory and just feed back the outputs from the CLU back to the memory? Well, the problem is that when you do that, this is the address and this is the data, and there's always going to be, you know, some period of time where the data is not stable when the address changes. So the problem is that if the address is, say, something, then the data comes out and it's not stable for a certain period of time. That means that the data here is not stable for a certain period of time, and when it gets fed back, that means that the address here is not stable for a certain amount of time, which means that the instability just sort of feeds back on itself. Eventually it might settle down into the correct state, but the problem is that we don't, that's not necessarily true. So that's why I had to go with a layered structure like this. So 3 layers of memory, then we get the output. The output goes through a buffer and gets put back on the bus, the destination bus. So the reason that I have these buffers here instead of going directly to the memory is that I have a backplane, which means that every card adds capacitance to each line. So of course, by putting a low input capacitance buffer in here, I'm able to reduce the overall capacitance, which allows the bus to be driven properly. The disadvantage of that is, of course, that each buffer generates, leads to a propagation delay. So, oh well. So there's a propagation delay from here, and then there's one here, one here, one here, and one here. So overall, it's going to be, 5 propagation delays. And I think these memories are like 10 nanoseconds. So 10 nanoseconds, 10 nanoseconds, 10 nanoseconds, and I think the typical propagation delay of a buffer is like 7 nanoseconds or something like that. So, we're talking 44 nanoseconds, which, isn't great when you consider it's about 50 nanoseconds, which means that the most you could ever do in adding would be, say, 20 megahertz. It really sounds small. It really sounds low, 20 megahertz. Compared to today's gigahertz chips. But the only reason that they were able to get to gigahertz range is that it's all integrated on one chip, and all the features are really, really tiny and small. So your propagation delays are down in the picosecond range instead of the nanosecond range. That's just the way it is. Also, these chips have to have buffers internally between the input and the output. For signal conditioning, because obviously when you're inside a chip, and you're just and exactly the logic that you're feeding inside the chip. Well, you don't need a generic output driver, so they dispense with all the intermediate output drivers, and that's what really contributes to the propagation delay here. There are other ways to get faster propagation delays, things like ECL, I squared L, all sorts of different types of logic. They all take a lot more power once you get into the higher speeds. I'm just using CMOS. So anyway, that's the rough calculation. Let's get soldering. First, let's check the chat, see if there are any questions. Let's see. Is there a rhyme or reason to when pins are 0 indexed and 1 indexed, i.e. A0 versus S1? Generally, I don't know. I mean, I always number them starting from 0 because that's just the way binary works. If you've got a large bus, the first signal is going to be named 0. I have actually seen chips where they don't do that. I'm looking at you, TMS 9000. They actually start from 1, which really made me angry in the face. So let's see. Yeah, in terms of like S1 and S2. Okay. So for example, I think on the 74138, which is a 3 to 8 decoder, 3-line to 8-line decoder, they have 2 enables called G1 and G2. In that case, the 2 enables don't form a digit. They're just 2 enables. So, you could call them G0 or G1, or you can call them G1 or G2. That doesn't actually matter. Where it does matter is when you're having, a bus of like data lines and address lines, and it's important to have them ordered correctly, and they represent binary numbers. So you have to start with 0. That's my explanation. I don't know if it's correct, but it sure sounds correct. All right, let me move the camera. Let's see. We have a black screen. You know why we have a black screen? I'll tell you why we have a black screen. It's because the infrared receiver on the input switcher of my video actually interpreted the moving of the paper across my ceiling light as a signal. So you can tell that that thing was not engineered very well. All right, so, okay. So anyway, here is the circuit that I will be soldering together. Now I have the fabrication list. Okay, fabrication list. This is the fabrication diagram that comes out of KiCad. So it tells me where all the chips go and what their orientations are. So I think that's like really important to see like the little diagonal lines which tell you where pin 1 is or where the dot on the chip should go. That's really important because often, when you look at a board like this, you will see, let's see if I can get something to point with. Actually, why don't I just put this under the microscope? Yeah. So you will see either a line for pin 1 or a dot for pin 1. I added these dots myself because I grew up with dots, not these fancy schmancy lines on footprints. But anyway, the dot tells you where pin 1 goes. So, but the problem is that that dot can rub off. It might not be printed by the PCB manufacturer well. So it's always good to have a fabrication diagram to tell you what each chip is, right? Because there's typically not really a great amount of room to tell you what that chip is. There is a designator, you know, U38, that's what this thing is. But then, you know, if you would have to look at a list of what U38 corresponds to. And instead I've got this, you know, nice diagram which tells you, let's see, where is U38? Am I holding this right? I think I am holding this right. There's U38 right here. There, U38. So, and you can see that the diagonal line tells you where pin 1 is supposed to go, and it also tells you what chip it's supposed to be, in this case a 541. Now I did an underscore A because I actually have different, not exactly different pinouts, but different designations for the 8 inputs and the 8 outputs. So on one, I have the 8 inputs going from 0 to 7, and on the other, I have the 8 inputs going from 7 to 0. Sometimes it's more convenient to do it one way so that you're not crossing lines. Sometimes it's convenient to do it the other way. So I actually have 2 different pinouts, kind of. So, you know, the underscore A designator doesn't actually mean anything once you're putting the chips down. They're both 541s. So, anyway, let's see. So, let me pull out the chat window. Let's see. Pop out chat. That way, I can see the chat. Great. All right. Wow, a whole lot of messages rolled in. It needs a clock, and Rob has no clock signal in his design. That is correct. This is, at least this section, is unclocked. It's basically just straight logic from input to output. The clocks come in when I decode an instruction, when I clock the result into a register. So there are clocks in the design, just not on this board. Let's see. The camera's focusing on faces. Yeah, I know. I just can't be bothered to remove that feature or to find out how to turn off that feature. I've got more important things to do. Okay, so let's see. What have we got? Well, let's get to soldering. So I've got... Oh, yeah, okay. Here's something else. Before I get to that, let me switch the camera. This is something I discovered recently. Okay. So if you look online, and I don't have the setup to actually show you the website, but if you look online for Hacko solder fume extractors, you will find some sort of a $70 or $80 item. Well, I looked at it, and it's just one of these fans inside a nice case, right? I picked this up surplus for like $5. It runs off of 12 volts, right? Now, the other thing that the Hacko fume extractor has is a filter. Well, I picked up these cheap activated carbon filters for like nothing, and they happen to be just the right size for my fan. And check this out. So I'm going to put this over here where you can see it, and then I'm going to plug it in and make sure that the air flow is going the correct way. Yes. There. That's my filter. It's fairly quiet. It's probably about as quiet as the Hacko units. And you know, you don't actually have to take it apart to change the filter. You just pull the filter off. Okay, so that was fun. So let's see. So I will be using, for now, this tip. This tip, it's just, you know, a conical tip. It's quite small. I'll be using that for the passive components. And then for the chips themselves, I will be using this, which you've seen on previous soldering videos. There, you can see that there's a little well inside there that holds solder, so this is useful for drag soldering. I also have this other one, which I've had pretty good success with. It's basically a knife edge, and you can use that for like QFNs, because the little tip here, the kind of chisel, gets right in between the component and the printed circuit board. So that's what I will be using. So I'm going to start with some of the passives. So I'll just turn on my iron to 330 Celsius. Now I'm using a Hacko iron. It's an FX 951, and I'm also using these shavings to clean the tip. I don't like to use a wet sponge, so yeah, surplus is awesome, isn't it? You can find all sorts of things, and all you have to do, you know, is be a little creative. You know, just put stuff together until you become inspired to, you know, actually build something. So let's see. Yeah, exactly. Everything is fine as long as the asynchronous logic is not taking longer than a clock cycle. So, of course, you adjust your clock so that your logic has enough time to settle. That's really all there is to it. And, you know, really that's no different from anything that you would call synchronous. I mean, you're always going to have a clock edge and then some logic and then another clock edge. So, of course, you know, you can't clock your logic so fast that the signals can't propagate. All right. Yeah, okay. I've got all of my parts here. Here are all of my parts. So I've got some resistors. Resistors are used, the resistors are used on signals that need to have a defined value while the system is powering up. So basically this sort of turns off all of the buffers so that you don't have multiple buffers feeding the same signal, that sort of thing. I've got my capacitors here, my reservoir, charge reservoir capacitors. Charge reservoir capacitors are used on every chip or every other chip, or, you know, I've seen on especially large boards like this one. This is a board with about 600 chips. It's a floating point array from a vintage computer. This is all TTL. It's not even CMOS. But yeah, so it's all TTL. And there are capacitors. Let's see if we can see that. Ooh la la. So if you see the capacitors there, you'll see that, you know, there's roughly one every 2 chips. So, you know, they didn't bother to put a capacitor per chip. And I did, which is probably honestly overkill, but you know, I don't really have a rule for, you know, when I can skip capacitors, so I just put them all on. Let's see, I've got an inverter, a binary counter. Okay, that's important because remember that I'm using the Cadet model, which requires RAMs or ROMs. RAMs are actually faster. And there's a boot phase where I do have ROMs sitting on the board. So there's a boot phase which has to load the ROMs into the RAMs. So for that I need the counters. Let's see, there's an OR gate in here. This is basically most of the chips on the board. It's a 74-541, a non-inverting buffer, 8 bits. Okay, I've got these 256K SRAMs, those are the memories. And then I've got 2 types of E² proms. One is a 64K and one is a 256K, because I found that that one of them actually didn't need as much data as the other, so I just used the smaller ROMs. There are also here, these are the sockets for the ROMs. Unfortunately, I don't have the sockets. I was going to go to the surplus store and see if I could find the sockets, but I didn't get around to it, so oh well, I'll have to leave that until later. And also, sprinkled throughout, I think I just have like 3 of these electrolytic capacitors just to provide a larger reservoir local to the board. So what I'm going to do is start with some of the passives, maybe just in like one area, and then I will put the chips down. And typically when you solder a board up, you want to start with the lowest laying components and then gradually work your way upwards, so that you can, you know, so that there's room to solder things in. All right, so capacitors. Actually, let me put down the resistors first so that I can get those out of the way. because I know there's only like 3 of them or 4 of them. So, and usually what you can do with your fabrication diagram is you can actually color code them with little markers, so that it's easier to see where it is instead of, you know, searching around to find, you know, the 2 resistors in your huge board. So let me go ahead and, let's see. Let me just check the chat, see if there's anything in here. Yeah, the 74F181 can supposedly go over 100 megahertz. That's actually pretty good. And that's an 8-bit ALU, isn't it? Interesting. Well, the problem is that then I still need to carry lookahead unit. Otherwise, I'm just rippling things, and you know, you sort of ruin your whole advantage right there. You know, and considering that my full adder is 10 nanoseconds, it could also theoretically go up to 100 megahertz. It's just that it's not very useful unless you connect it up to something else. So, let's see. Okay. Yeah, that's right. Cadet was like an IBM thing. So, okay. Let's get to the board. Okay. So here is a nice section that I can do. I said that I was going to do the resistors first. So let's go ahead and find some resistors. I think they're all down here somewhere. No. Unless I put them on the back of the board. I put one on the back of the board. Oh, here's one. There's one. R1 and R2 right there. So I'll do those. So let's go ahead, and the iron is fired up. I will go and take my small solder. And I also have some flux. I am going to be using Kester flux. I have been using MG flux, and I would just like to try Kester just to see how it goes. The MG flux gets pretty sticky, which, I mean, it's flux. I guess it's supposed to be sticky. I just was kind of hoping for something a little more liquidy. So let's try it. I don't use no clean flux because I found that, I don't know, I just don't like it very much. So I think the tip on this is dry because this is a totally new pen. So let's just push the tip until we get some flux coming out. Ah, see, it's beginning to, there we go. Flux, flux. Okay, cool. Cool. All right, so what I'll do is just put a little solder on one of the pads, and then, let's see, the best way to do this is like this. Focus a little better, maybe. All right, got my resistors here. I hope these are the right ones. I actually didn't order any of the 10Ks when I made my order for all the parts, because I figured, oh, I have 10K resistors lying around somewhere, and I found these. And they're 0603s, which is the right size because I only use 0603s. So, yeah, they're the right size. You never know. And I'm having a little bit of a hard time. You know what? Razor blades are one of the most useful tools you can have in your toolbox, because then you can do awesome things like that. Now I can get at the resistors. Okay, so I'll take a resistor. And promptly lose it. Where did it go? That's not a great start. There it is. Right. Unfortunately, my tweezers are a little sticky. Oh, I know what I forgot. I forgot to get some isopropyl alcohol. One moment, please. Yeah, always a good idea to give your board a good rub down with isopropyl alcohol before you start soldering it, just to get any oils off of it, which I forgot to do, but will do, I promise. Also, I am going to clean the tweezers, which are probably covered in flux. There we go. Okay, now. Where'd my resistor go? I don't know where it went. Alright, well, resistors are cheap, so I'll just get another one. Wait. Alright, so let's just do that. So what I can do is, can I zoom in on this a little bit? Focus on it. And focus the camera. That's nice. Okay, cool. Oh, it was in the footprint for the ROM. I moved it. Where did it go? I don't know. I was rubbing the board gently and it should have just fallen on the table, but nope. Alright, so what I do with passives is I just sort of slide them on like that. Just like that. Done. Well, except for the other side. But, you know, the loss of that resistor really annoys me. But, you know, I just have to accept that it's gone. And that they're really a fraction of a penny each. So, flip that over. Now you'll notice that this resistor says 01C. Doesn't say anything about it being 10K. So you just have to sort of, you know, I guess you could Google it, and 01C is probably some manufacturer code. Or maybe it's C1, no, I'm pretty sure it's 01C. But, you know, at least the manufacturer marked it. If these are capacitors, no markings. No markings, you lose. Alright, so now that I've done the two resistors, I will go ahead and rub down the area that I'm going to be working on with some isopropyl alcohol. So let's see, I probably want to work on this area here from C17 and U17 all the way up. So I'm just going to give that a little alcohol bath. Nearly all the oils are gone. And I'm using a clean Q-tip or cotton bud or cotton wool bud. But yeah, because I don't want to use the one that I would use to clean off flux, because that's all fluxy. Okay, so for the passives, of course, I will do exactly the same thing, just flux. There's flux. Where's the capacitor for this guy? Probably on the other side. So flux, and I may as well just do these as well while I'm at it. So, and this one, sure. Okay. So we put a dab of solder on there. Now, the coating that I got for these pads is Hazel, hot air solder leveling. Hot air solder leveling. So basically there is a little bit of solder on this already. So I can sort of melt it a little bit. But there's not a whole lot of it. So, you know, I just put a little bit more on, because I'm a little moron. Okay. And I'll just grab some capacitors. Just dump them out. And grab one. So here's one. Great. Fantastic. Thanks for showing up late to the party. All right, I'm going to put this one aside on something white so that I'm not going to lose it. Wowzers. Okay. That capacitor. So you can see that the capacitor has no markings. So if you wanted to reverse engineer a board, you could try to measure it in circuit, but usually what you want to do is just desolder it. And then measure it out of circuit. That's not a great angle, is it? I think I should turn the board around. Banta. C19. Unfortunately, my hands are slightly shaky because I just had some coffee. So, tip for engineers: when you're about to do some soldering, maybe don't caffeinate yourself beforehand. See how wobbly this capacitor is? It's kind of wobbly. I guess they're not really quite flat. Happy Turkey Day. Is that today? I thought it was tomorrow. Tomorrow being Thursday. Today is Wednesday. I don't know. I don't celebrate Thanksgiving because I have no friends to go to. And my family doesn't live in the area, so yay for being an introvert. Instead, I get to spend my time with all of you. Not that that's a bad thing, because it isn't. This is a mistake. Yeah, do that side first, then this side. Okay. there just wasn't enough solder on that one. And C28. Okay, are those all the ones that I wanted to do? 1, 2, 3, 4, 5, 6, 7. Sure looks like it. All right. Solder up the other sides. Now the reason this is taking, the reason you can see that it takes a long time to melt is that first of all, there is no solder to form a nice heat bridge. And second of all, this is probably connected to the ground plane, so that's why it took so long to melt. That's why typically what I like to do is apply the solder to the iron first, where it will melt immediately. Then the solder drips onto the pad, where it forms a nice way for the heat to get to the pad quickly. So, all right, let's do these 4 chips. We'll start with U17, and I'll orient this so that the dot is like that. And let's flux this. Let's just do the one. Okay, now all of these chips, I know for a fact, are buffers. There are only a few glue logic chips, and the RAMs are pretty distinctive. They're just these, you know, sort of longer chips. Long chip is long. So let's see, here we go. I have, how many of these are in here? 200. That's probably way more than enough. All right, let us get a chip out of the bag. Let me use the razor blade, because razor blades are awesome. Just don't play with your razor blades absently while you're on the phone. I learned that lesson the hard way. Here's my chip. Orient it the right way. Okay. So again, what I usually do is put it down. Oh, I need to change tips, don't I? All right. Let me turn the thing off. And so I just use a piece of cardboard to pull the tip out because I'm impatient and I don't want to wait for it to cool down. Let me get my tip holder ready. Great. All right. So. That makes it really quick to change tips. So, all right, turn the thing on again. All right, so since I'm going to be dragging down the line, I want to orient it this way. So what I do is now, so I've fluxed the pads. So what I'm also going to do is I'm going to flux the pins as well, so that now the solder can flow up to the pins and down to the pads as well. And now what I do is I simply load up the reservoir with some solder. Looks like I already had some on there already. Hold the chip in place. Place it very carefully. Make sure that all the pins are lined up with all the pads. And sometimes what I'll do is I'll just sort of, there we go. And then very gently, so that I don't move the chip around. Pretty neat, huh? Done. I think that may be a soft solder bridge, but all I have to do is touch it to get the bridge away. That's all there is to it. See, the idea is that there's kind of a bead of solder formed by this well, so that as you drag the solder across the pins, the flux will allow the solder, or the fluxed metal will actually draw the solder onto the metal and not onto anything else. You may get bridges, but those bridges can be easily removed. So, get the other side. Flux. Reservoir. So you can sort of see that the solder kind of forms this little bead. And then you do have to get the right angle on this, and it takes a little bit of practice. And if you don't do it for a while, you sort of lose that physical knowledge. All right, there we go. Done. That was pretty easy. So now just to, now I can inspect it, you know, by sort of zooming in and looking at it and seeing that, you know, for the most part it's pretty good. But what I'll do is, yeah, it is kind of like a fountain pen. I love fountain pens. I'm going to take my dirty Q-tip and just clean that up. Okay, I didn't get any isopropyl alcohol. So I did order from eBay some Kim wipes and a nice little alcohol dispenser. So there we go. A nice clean chip. Very nice, except for this part. A little too much flux there. Alright. I know you can more clearly see the joints. They're nice and shiny for the most part, and that's pretty good. Now, normally what I would do if I had good access to these signals, I would actually test the continuity by touching on top of the pin, but I don't think that I'm going to do that. I'm pretty sure that this is all pretty good, and if it isn't, well, I'll catch that during testing. Then I can probe, because there's just way too many signals on this. Anyway, let's do another one. Flux. Yeah, I do like this flux. It's certainly more liquid. Then again, I've had that other flux pin for years, so you know, maybe that has something to do with it. This is a new flux pin that I just got. Alright, let's orient this. First of all, orient it the right way up. And second of all, orient it according to the dot. So it'll be like that. Okay. Just flux the pins. Load up some solder. Get the chip exactly where I want it. And done. A bit of a bridge there. Easily taken care of. Alright, other side. Flux. So these chips are don't have as fine pins as some of the chips that I use, and it's really careful. You have to be really careful when you use the flux pen, not to, like, you know, drag it roughly. Typically, what I do is I just sort of dot the fine pins like that, because the fine pins can bend really easily, and then you're not going to be very happy. So. Okay, let's do the next one. Yeah, the alcohol, yeah, it was kind of fun when the alcohol revealed the lettering on the chip. I've seen Dave from EEV blog just sort of put some saliva on his finger and do that, but yeah. The interesting thing is that sometimes when you get boards from China and they want to sort of hide the number from you, they sort of scrape off the top. Sometimes they don't do so good a job. So you can actually take some saliva or some alcohol and put it on top of the chip and then reveal the numbers. So. That's over there. Okay. Let me switch to the second camera. I just had an idea. So the problem with using this flux pen is that every time that I want to, first of all, you should put the cap on it, just like you should put the cap on all markers so that it doesn't dry out. Second of all, so when I put it down, I put the cap on. When I take it, I have to remove the cap, so I have to do it, you know, one-handed like this, which is kind of, you know, inconvenient. Because what I do is I just sort of take it and then drop the cap, and then I have to pick up the cap with two hands. Well, you know, why don't we just like make a thing that sort of holds the pen from the cap like that, and that way I can pull it and just put it down one-handed. That would be a neat 3D printing, or, you know, actually just some hot glue would work. You know, just take a piece of metal, glue this thing to it, and then, you know, you're done. The only thing with hot glue is that you have to be careful not to get any alcohol on it, because alcohol will actually disrupt the bonds on hot glued stuff, and the hot glue will just come right off. Tip, in case you're ever trying to clean up hot glue from your kitchen counter. So let's see. Solder up this chip. It's on the right way. When you get the right angle, it's really satisfying. Pretty cool. Next one. So I'll do this next one, and then I'll do this RAM chip, because I really do want to get to the RAM chip, because that's kind of a funny shape. The pads, you can see, are also thinner, because well, are the pins really that far apart from the other ones? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I think the pin pitch is the same. It's just that these pads are fatter. I wonder why that footprint looks different then. Anyway. All right. Chip. Put it the right way around. So dot goes here. Oh, I think I ran out of solder. That's annoying. Luckily there was enough to sort of tack it down. Alright, let's do this one, U38. So that is an SRAM. Put some flux on. So I'm interested to see how the thinner pads are going to work. SRAM. Well, I suspect the SRAM is probably quite delicate in that it doesn't respond very well to being handled roughly by humans with their wet, capacitive, charged up hands. And really, I suppose I should be grounded when I'm doing this, but I don't know. I can't be bothered. Okay, so the interesting thing about this chip is that pin 1, you can see, is in the middle. It's not on the corner. So that's why. There's a dot here. Did I do that? But there's another dot over here. So in any case. Oh yeah, and look, there's in the corner, so there's a pin 1 marker which is printed, and then in the corner is where the resin mold was indented. So I guess that's 2 ways of telling which way the chip goes. Oh, that's interesting. There's also this weird semicircle. So that's 3 ways of telling how the chip goes. They're really not fooling around. And that's a good thing. Well done, ISSI. Alright. Now it's important to get the pins lined up very well with the pads, because they're quite thin, so there's not a lot of room for error. I think I ran out of solder on that one. So let's just add some more. And hold the chip. Yeah. Going over your pins twice, I've found, is a really bad idea. I think I just need more solder. I guess I was a little miserly with it. Yeah, I just want to get these pins. Okay, great. So again, the key to this really is to make sure that you flux the pins as well as the pads. Because if you don't, then the solder isn't going to flow very well. There we go. Okay. All right. Let's see. Could do this next one. U37. Now I don't have to do the capacitor next to it right now because there's enough room. There's enough room down here. Is this a lead-based solder? Yes, it is. You bet it is. None of that lead-free crap for me. Besides, I'm not an electronics factory, so I'm allowed. And besides, it's not the lead that's bad for you, it's the flux fumes. Just don't eat the solder. And I guess for recycling, again, these are one-off boards, and this is the least of anybody's problems. So anyway, that's my justification. What's yours? I only breathe lead-free. Yeah, sure. Except you don't breathe the lead. It's really a recycling issue. So the real problem is that when you throw these out, basically the lead goes into the landfill, and then the lead leaches into the land and possibly into the groundwater. So that's the real reason for lead-free. It has nothing to do with fumes. I think I have enough solder on that to try it. So sometimes what I like to do is just push down on the chip to make sure that I'm not holding it at a weird angle. So if you'll notice, what I've been doing is actually holding it on one pin and waiting until I see the solder flowing. Then I sort of know that I'm at the right angle, and I guess, that I'm at the right angle, and then I can just drag down. So that seems to save some time. Here's another one. Let's do that. Recycling is a myth. Yeah. Recycling doesn't really happen. It all goes offshore. And the sad part is, some of it just gets dumped in the ocean. Because money. And here is where I could go on a rant about late-stage capitalism, but I'm not going to. I can't wait until we have nanofabricators, which I think is scheduled to come in around 2035 or so. At least according to my prophet, Ray Kurzweil. Here's one we could do. Extracting metals, yeah. Actually, there's this guy on YouTube. I haven't actually watched him in over a year, but he, I don't know if I don't know what his channel is called even. I think I subscribed to the guy's channel, and I haven't seen like any recent videos in like a year or so. But anyway, he takes you know, boards like this or equipment, and he basically tears it all down to its components. And it's like he takes the tantalum capacitors and puts them in a box, and then he takes, I don't know what he does with the electrolytics, but you know, he'll take like the useful chips out and he'll put them in a box. He'll what else will he do? I don't know. He does things with like the metals and stuff like that. Like if there's a transformer on it, he will take the transformer apart and melt down the wire for the copper, and then just throw the copper in a box. You know, and you know, you don't make any money out of it, especially on that scale, but you know, I'm sure that if you were to scale that up, and if labor were free like it is in some parts of the world, essentially, you could make money off of it. But it was pretty neat to see, you know, how he sort of took things apart and showed you, you know, oh, here's some plastic, and here's, you know, this metal, and here's that metal, and, you know, we can melt it down like this. And he had a little crucible sort of thing going, or metal refractory, or whatever you call it. A metal melter. But it was pretty neat. All right, here's a chip that I could do. All right, this is U2. Which I associate with rock, but, you know, that's just me, because I grew up in the 80s. That was me. I grew up in the decade of greed. Greed is good. Not that I believe that. I'm just saying that that's what they called that decade. All right, so there's U2. So now I do have to look up what that is, because that is not a buffer. So if I just overlay this on top, we see that U2 is a 7404 inverter. So let's go grab the inverters. Okay, here's one. So I also had to be really careful to get the low voltage CMOS versions. So this is an LVC. It's important not to get a 74C04, because they're not really designed to work with 3.3 volts. Not really. I mean, I'm sure you could get them to work like that, but, you know, the voltage levels are a little different, so. This one just says LC, but it is an LVC, I know that. Okay, so set the wrong angle. This way, right? So you can see that this one doesn't have a printed pin 1 marker, but it does have the indentation in the plastic package. So that's just as good. Do I have enough soldering here? No, probably not. So the nice thing that I found about having a temperature-controlled iron, especially the Hackle, is that in the old days, at least with my old iron, you would put solder on the iron, and if you left the solder on without cleaning it off, it would just basically burn. Or I guess maybe that's not the solder, but the resin in the solder would burn, and then it would ruin your tip. And I found with these irons that you can just leave the solder on, and it's perfectly fine. Probably because the temperature is set correctly. 330. Why did I do that? Oh, I ran out of solder again. So I do have a bigger tip with a bigger reservoir, but I don't know. I think for these pins, this size is the right size. So speaking of hot air solder leveling, okay. So first of all, if you don't subscribe to Strange Parts on YouTube, subscribe. He has a video where he takes you through the JLC PCB factory, which is where I got my PCBs from. I didn't actually know what hot air solder leveling was. I mean, I knew what it was, but I didn't know how they did it. Well, basically they dip the board in solder, and then as they pull it up, there's like this fan that just sort of blows all the solder off of it. Didn't seem very level to me, but apparently that's the way the leveling works. So that's kind of neat. Anyway, the other coating is ENIG, or ENIG, which is electroplated nickel something or other. And that is what is recommended when you have fingers like this. Now you'll notice that these fingers are all Hazel. And that's not great from a reliability, well, not a reliability standpoint. That's not great for an insertion cycle standpoint. So if I put this into a slot and then pull it out and put it back in and pull it out, eventually these things are going to wear off, and then the connection is not going to be reliable. An ENIG coating is what you want for fingers like this. And unfortunately, you can't just ENIG coat the fingers. You have to ENIG coat all of the pads. So, and then you can put gold plating on it, which increases the reliability by multiple factors. So what JLC PCB does is they will gold plate the fingers, but only if the coating is enig, because I guess, well, you can't actually stick gold to solder. It's not a great idea, I suppose. Let's see. What about this one? Let's do this one. Oops. So I have to say this homemade fume extractor is working absolutely a treat. And I'm very glad not to have spent the $75. Okay, let's take a look at what U3 is. U3 is a 7432. That's an OR gate. So let's go grab the 7432s. First of all, let me put away these guys so I don't have them hanging around. Put them in the right bag. Always be cleaning. See, I have this roll of things, and now I don't know what they are. Well, I do know what they are. They're the 10K resistors, but that's only because that's the only resistor that I have. So I should have put them back if I could find the bag. Here we go. Here's the bag. And the label. Okay. Now they don't get lost. And also it's a good idea to just have a cardboard box or a plastic Sterlite bin to put all of your components in for one project. When you're done with that project, then you can take all the components out of the Sterlite bin and throw them into a cardboard box, just for your, component stash. And it's important to label your cardboard boxes with what's inside. Not every single thing that's inside, but keep them separated, like resistors in one box, capacitors in another box, say logic chips in another box, memory chips in another box. And come on, everybody has a lot of cardboard boxes because everybody shops at Amazon, don't they? Anyway, yeah, cardboard boxes are easy to come by, so just use them. Alright, so there is my little thing. LVC. This one is an LVC, not an LC. But so there's the little indentation mark. Who is this from? I don't recognize the manufacturer. Let me take a look at the label. It says Nexperia. It's an NXP part. Interesting. Why doesn't it say NXP on it? Well, I guess they don't have to. Why Stephen King solder things? Is this the first part of a joke? I don't know. Why does Stephen King solder things? Trying to think of a punchline. Because his horror is so metal. Sorry. the last 2 pins. Okay, so here's an example of where I don't want to put these 2 chips down, or at least I don't want to put one of them down, because this capacitor is right between the 2 chips. So I won't really have room to slide it up and down like this. I would have room to slide it this way, but I prefer to do it this way. So I'm not going to put these 2 chips down. In fact, I'm not going to put any of these rows of chips down. What I will do is put some more SRAM down. Here's one. There's a protruding solder clump on one of the pins, probably on the one that I just did. Probably that one, but that's okay. As long as it doesn't, like, protrude across the pins. I think that's what you're talking about. A little hard to see now. I don't really see any bridges. Let's see. Yeah, I'm looking at it through the microscope. It's a little better to look at, but no. That might just be the flux, so let me just do a quick cleanup. Left side. No. There's nothing there. Again, let me clean it up, because it's sometimes a little easier to see when all the resin is not there. Oh yeah, I sort of see what you mean, maybe. This pin right here, that isn't touching, so I'm not too concerned. In fact, I'm not concerned at all. But, you know, I may as well try and make it a little cleaner, I guess. There, I did it. So, yeah, that works. But yeah, you could definitely see it a lot better once you clean all of the flux off. So, anyway, yeah, it is definitely easier for me to see the board, simply because I'm looking at it in stereo and you're looking at it in monovision, which isn't great. But yeah, but that you spotted that tiny little thing really well, so obviously the camera is doing something for you. Okay, let's zoom back out and go to, let's say, U28. Let's get this focused. Great. All right. U28, another SRAM. Flux. Oh, you know what? I don't think I cleaned this off yet. May as well just do that now. I also ordered from Amazon, you know when you go to the doctor's office and they have that neat little, like, alcohol dispensing pumps? Just before they're about to jab you with something sharp and painful. So I bought one of those. I had to pay like $7 or $8 for it. And I'm like, surely I can get this cheaper from China. Because really it's just a glass bottle or a plastic bottle and a pump. So I went on AliExpress And sure enough, you could get them for like $2 or $3 a piece. But the shipping was the killer. It basically brought the price up to what I would pay Amazon to have it shipped 2 days prime. So, yeah. I just bought it from Amazon, who probably bought it from the Chinese suppliers. So, did I put away the chips? Yeah, I did. Okay. So where are the SRAMs? SRAMs. Oh no, there's nothing in the bag. I didn't clean it up. Well, crap. It shouldn't be that. Ah, here they are. Okay. There's the dot, there's the dot, there's the dot, and there's the dot. So this is the right way around. This capacitor got in the way. Alright, there we go. So I was holding this at, I guess, too shallow an angle. I suppose I should have done maybe this. It's quite tight, but I think I got them all. I will, there's a little dot of solder here. Solder. I can just pick up. I'll inspect this afterwards. Oh, there's a solder bridge. My first one. Let's focus in on that. Let's focus in on that mistake. And here's how to get rid of it. First of all, clean your tip. You don't want to add more solder to a solder bridge. That's kind of stupid. Second of all, heat one of the pins up. Let's heat this pin up. Sometimes that'll just draw the solder in, and sometimes it won't. The other technique is to just heat both pins up and pull. That's not happening. So the final technique is just to take some desoldering braid and put some flux on it and just press it against the pins, which is kind of dangerous when you're dealing with extremely fine pitch. Oops. The board fell out of its holder. One moment. Alright, so This can be dangerous when you're dealing with very fine pitch pins, because when you press, you tend to damage the pins. This actually seems to have left enough solder, so I'm okay with this. I will go ahead and clean it now. So the problem with such high magnification is that you can't really focus on the entire thing. You really have to select a plane of focus. So I think that worked out pretty well. Let's inspect both sides. Yeah, so I got one of those alcohol dispensing things from, or I'm getting one from Amazon, and a bunch of Kim wipes. And I think that's better than these little, you know, cotton buds that sort of leave cotton threads all over the place as they snag on things. Alright, so the other important thing is, and this is another reason why I got this alcohol pump thing, is that I just have the alcohol in a bottle. And number one, you take the lid off, and you tend to leave the lid off, and then your hand knocks it over. The other thing is that isopropyl alcohol absorbs water, so you never leave the lid off of an alcohol bottle. Insert joke about drunks here. I'm really liking this this flux. Again, I don't know if it's because it's new flux. What I really should have done is gotten a new MG flux pen and then compared the two. Because it's not really a fair comparison to compare one flux pen that's old with one that's fresh. On the other hand, this one, let's see, where is it? Right here. It has a date of expiration. So here's when it was manufactured, May of 2018, and it expires 2 years later, I guess. So, and the MG pen didn't have any such markings on it. And I'm like, I know it's a little more expensive to have custom labels made like that, but it would be really nice to actually not have to write all that stuff down yourself. So in fact, I don't know how old my pen is. I don't know why that didn't go as well as it should have. Did I put flux on the pins? Well, if I didn't, then this would be an abject lesson on why you should put flux on your pins. think I didn't put flux on the other side. So you can see how more difficult it was. Let's see. Oops. It goes the other way around. I should tell a story. Okay, here's one. I mean, like, you know, a thing that happened to me kind of story. So I got me a Tesla. I have a Model 3. It's an awesome car, by the way. It's dual motor. And it's so fast. Oh my god. Anyway, so I wanted to install a charger in my garage because just charging off a 120 or 240 circuit doesn't give you a very fast charge speed because of the way the current works. But Tesla sells a charger that it's basically a smart charger. You know, it can tell when it's plugged in. You can set current limits, all sorts of things. And it's nice because you could set the current limit based on the fuse or the current capacity of the circuit. So anyway, I get it home and I'm like, you know, I know electronics and I've worked on hot circuits before, hot 120 volt circuits. So I know how to do this. So I already had a 240 circuit and socket in my fuse box and installed in my garage. So I'm like, okay, all I need to do is pull the socket out, or uninstall the socket, and wire up the charger. So I open up the fuse box, I remove the 240 fuse, and I start pulling the wires from the socket out of the fuse box, and you know there's 4 wires there, a neutral, 2 hots, and a ground. And the ground is just this, you know, solid copper wire. So I'm pulling the wires out, and all of a sudden, bang, and all the lights go out. So what happened was, as I was pulling the wires out, the copper wire was flailing around and it hit the main bus bar. And I'm like, oh, okay, I just blew the house breaker. And, you know, usually the house breaker is right on top of the fuse box, or right above all the fuses in the fuse box, if you have one fuse box. And I'm looking, and, well, there's no house breaker. And I'm like, great, now what? I'm looking all around to see if there's any other fuse box. No, that's it. And then I realize, well, I'm in a condo, and there's actually an electrical closet where all the house fuses are for all the condos. But it's a locked closet. So I'm like, okay, well, so how do I get in, right? It's just easy. I just, flip the breaker. So eventually I emailed the condo association people. And our condo association is maintained by, not people who are on site. So I email them and I explain what happened, and I say I need to flip the house breaker. And they said, oh, okay, well, we can either be there on 4 days from now when we're visiting and do, and flip the circuit breaker for you, or if you do it yourself, here's the combination to the key box where we keep the key. And they kept the key in the same key box that the common clubhouse key is in. So I'm like, oh, okay. So I got the combination. I went to the key box. I opened up the key box. There's no key. So I sent them an email with a picture of the empty key box saying, there's nothing in the key box. What the hell, guys? In the meantime, I was without power for, a day by that point. So I finally just decided to take matters into my own hands, and I picked the lock on the utility closet in 15 minutes and flipped the house breaker. The end. Coda, the reason that the key was missing is that apparently the person who had been using the clubhouse wanted to get in and out several times and just took the key with them, not realizing that there was also a key to the utility closet. So, anyway, that's my story, and I'm sticking with it. Alright, well, I guess there's not really much else that's interesting on this board to do. Like I said, I don't have the socket for these PLCCs. Oh yeah, so about the lock pick. So, I know how to pick locks. So I was working on, getting all the pins set correctly. And then I realized that in my kit I had what's called a city rake. And it's basically a wavy piece of metal, basically, that works to open cheap locks. Because what a city rake does is you stick the wavy piece of metal into the lock, and then you jam it in and out and in and out and in and out. And if the lock is cheap enough, the pins go up and down and up and down and up and down, and eventually they open. So at first I was trying the single pin technique, and that wasn't working. And then I used the city rake, and it opened in like a minute or less. It was really funny. Okay, so anyway, like I was saying, there's not really much that's interesting here. I don't have the sockets for this. Besides, that's just through-hole soldering. That's not very interesting. All that's left are a bunch of passives, really, and the rest of the chips. So I guess I will call it a day. Let me go ahead and switch. Yes, I will call it a day. And I guess that's about it. So anyway, here's what the board looks like now. So that's kind of nice. You can see that it's coming along quite nicely. So all I have to do is solder one of these together, and then a second one, And then my friend will be able, he's written some Python code in order to test this. We use on the tester an FT232H breakout board from Adafruit. And the annoying thing about the Adafruit library that's supposed to be for it is that it's only for Python 2.7, and it's only for a very old version of the FTDI library. Luckily, someone has set up another GitHub repository with the change that's required to get it to work with 3.6 and the latest version of the FTDI library. Unfortunately, the latest version of the FTDI library isn't compiled for 3.7, so you're stuck with 3.6. Luckily, he does include information on how to compile the FTDI library, which means that I could get it running in 3.7, which I'd like to do at some point because I like using Python 3.7. But yeah, don't say ugh, Python. It's a perfectly reasonable language for writing quick tools in. I'm not going to pull out my Java compiler or my C compiler just to write some tools. Python is a very high-level language, and there's nothing wrong with it. Now, if you would have said JavaScript, I would say ugh. So, anyway. Interesting. Okay, yeah, I don't know about the Sci5 unit. That's a RISC V processor. There's an Adafruit library for Sci5. Well, anyway. What was I going to say? Oh yeah. So if you know a little bit about Python, you could probably, go in to the Adafruit libraries and put some log statements in there, and then find out what's going wrong and then fix it. And obviously, between 2.7 and 3.6, there are a few changes, not a whole lot, just change print statements and be aware of the difference between byte and byte arrays, bytes and byte array. And so there are some differences in the library, but for the most part, I haven't really found anything that's really, really different, that's like completely incompatible. Every library, at least that I've seen, that isn't insanely complicated, will work between the two versions as long as you take care of just a few things. Where was I going with this? I don't know. Anyway. I think that's about it. So, thanks for watching. So I appreciate all of you keeping me company for the past 2 hours. Wow, okay. So, the microscope, if you watch the live stream that I did yesterday, it's all about this microscope, which I just got from Shenzhen, and the camera that's on it. So you might want to sort of look at that video. I guess that's about it. So again, thanks for watching, thanks for keeping me company, and I hope I've kept you a little bit of company on this nice day in the Bay Area, which is now free of smoke from that awful, awful fire. So my lungs were doing some serious hacking, and not the good kind. So anyway, take care. See you on the next video. And oh, just before I go, hang on. I have to show you a cat. Yeah, it's about that time. Right, kitty? All right. See ya. Oh, what was the YouTube channel again? There was Strange Parts. And let's see, what other YouTube channels did I mention? There was one guy who did recycling. I have no idea. Just look for like recycling electronics tantalum, and you'll probably find it. Felis catis. Felis. Feles, feles, semper feles, as my Latin teacher would say, as I went off on another rant about how much I love cats in Latin. Feles. Amo feles. Alright, yeah. See ya.